We have a free body diagram given to us. It's a 5 kilogram box. It's on a rough surface, so that means there is friction. We are told it's being pulled at constant speed, so that means the acceleration is 0 and the F net is 0. We've got our 30-degree angle, theta, coefficient of dynamic friction, so mu d is 0.30. We want to know the tension in the string. So setting up our Newton's second law, F net is the sum of the forces, and that is ma. And our forces that we have would be Tx minus the force of friction. Now Tx we're going to need to obtain from trigonometry. So that's going to be cosine. Cosine of 30 is Tx over T. So Tx is T cosine 30. So we have T cosine 30. We know the acceleration is 0, so that is 0. And the force of friction. The force of friction is mu d times the force normal. Now the problem we have with the force normal is that there's a component of the tension upward, Tz, which reduces it. And this is intentional that they've drawn this normal smaller because there is this additional Tz part. And so we use the sine. Sine of 30 is Tz over T, and Tz then is T sine 30. And what we also know vertically is that the net force is the sum of the forces. And Ma is mg minus Fn minus Tz. And so we end up having mg is equal to Fn plus Tz. And mg is 5 times 10, or 50. And Tz is T sine 30, which is 0.5 T. Sine of 30 is 0.5. So the force normal then is 50 minus 0.5 T. So that takes us to our mu dynamic, which is 0.30, and the force normal is 50 minus 0.5 T. Distributing the 0.3, we get 15 minus 0.15 T is the force of friction. Putting that into place. Now the cosine of 30 is 0.866 minus 15 plus 0.15 T. Adding those together, we end up with 15 equals about 1.02 T. So T then is 15 divided by 1.02. And 15 divided by 1.02 is about 14.7. And you can see that the closest number we get to that is 14.47. And this could be due to the using 10 versus 9.81, but by far and away the closest one is 14.47.